Okay, welcome back to another video on PDEs. Now we solve a wave equation. The steps are just the same, separation variables, just some new things to do, but everything is just the same procedure. Nothing is new. We have the boundary conditions here. We have the boundary conditions here, and we have the initial conditions. Okay, let's start by separating. First, we have u equal to x, t, the same procedure. We have the first derivative, we have the second derivative. After we do that, we still remember second derivative t, and we have t squared, we have x t double prime. Okay, I'm just going fast in this part because we've been doing that in these last videos. I think three videos we have been just solving using separation variables. So I'm assuming that you watched the previous videos. Okay, now I will just sub to the original equation. Then I have a squared. Second derivative of u is gonna be x double prime t equal to x t double prime. Divide both sides by xt, then you have a squared x double prime over x equal to t double prime over t. Then I just want to do x over x 1 over a squared t double prime over t. I'm going to separate both sides by saying that it is equal to lambda. And now we can just separate by putting x double prime over x equal to lambda and 1 over a squared t double prime over t equal to lambda. Then this is going to lead to x double prime minus lambda x equal to 0 and t double prime minus a squared lambda t equal to 0. Okay, now I have to evaluate the cases. I have case 1, if lambda 0. If lambda 0, then I have x double prime equal to 0 because lambda is going to 0, going to cancel this part, and t double prime equal to 0. Okay, by solving here, by integrating once, I have x prime equal to c1, a constant. By integrating second time, I have x c1x plus c2, like that. Okay, now I need to find this constant, c1 and c2. What I'm going to do is going to the boundary conditions. The first boundary condition is gonna be, again, x0 t equal to 0. Just leads to x0 equal to 0. Second boundary condition, pi t equal to 0, you have pi equal to 0. So you have these conditions to use to find C1 and C2. When I use the first one, C1 x0 plus C2 has to be equal to 0. Then you get xc2 equal to 0. X pi, when you use pi, c1 times pi plus c2 has to be equal to 0. But c2 we found that is already 0. So we just end up with pi c1 equal to 0, then c1 is 0. That means x is c1x plus c2, but both of them are 0. Then the solution, u xt is just, okay, x times t, which is just 0. This is the first case. Now, okay, we move on to the second case. Case 2. For this case, if lambda negative, I'm going to say, okay, lambda equal to minus alpha squared. So lambda negative. I won't do the third case where we find the hyperbolic cosine sign because usually they don't lead to the solution. So I would just stop here when I get sine and cos. Okay, by doing that, we have x By doing that, we have okay. Let me just isolate. We have second derivative. Then we have plus alpha squared x equal to 0. And we get twice plus a squared alpha squared t equal to 0. I'm going to solve the first equation. The first equation, the characteristic equation, just alpha squared equal to 0, r equal to alpha I. Then x leads to C4 cos of alpha x plus C5 sine of alpha x. So I need to find this constant again. We have the boundary condition, the first one, 0 equal to 0. When I plug this, when I sub this, 0 is going to be C4 cos 0 plus C5 sine of 0. All of this has to be equal to 0. Then I just get C4, 1. Sine of 0 is 0, so here gives you 0, 0. By isolate C4 is just 0. Then we get xx equal to C5 sine alpha x. Okay, now let's use the other condition. X pi has to be equal to 0. X pi C5 sine of alpha pi has to be equal to 0. Okay, here I'm gonna say C5 different than 0, then sine of alpha pi has to be equal to 0. It's not count. Then alpha pi equal to n pi. I'm gonna say n1, 2, 3, 4, and so on. Because if n equal to 0, everything just gives me 0, and I go back again to case 1 where lambda equal to 0, which the solution is just 0. So I will just start n, I will start 1. From here, alpha equals just to n. Then x equal to C5 sine sine of alpha is n, times x, like that. We just got this solution here. Now we need also to solve for t. Solve for t. Solve for t. This is one of the difference when you actually solve wave equation. You also have to solve for t. T, we have second derivative plus a squared alpha squared t equal to 0. The solution for this leads to, I'm going to say C6 cos of a alpha t plus C7 sine a alpha t. If you solve for this, because all of this is going to be some constant, I would say beta, and then you have to solve for that, and then just, okay. Now, that means this is the solution for t by solving. Then I have u xt equal to x times t from the separation. Then I have c5 sine nx multiply c6 cos a. What is alpha? Alpha is n. Nt plus c7 sine a and t, like this. Then u xt equal to, multiply this with this, I'm gonna just get one constant. I'm gonna say a, big A, c5 times c6, big A, cos a and t, plus c5 times c7, another constant, sine a and t times sine nx for n equal to 1, 2, 3, 4, and so on, like that. This solution is just for n equal to 1, n equal to 2, and 3. So I'm going to use the principle of superposition, which implies that the general solution is going to be summation n equal to 1 until infinity. Then the constant will also depend on n. I have an cos of a nt plus b, and it will also depend on n, a and t times sine nx. Okay, sine of nx. So this is your solution. Now you need to know what are these constants here. Okay, I go back to the initial condition to find the variables and to find this constant here, an and bn. So one of the initial conditions was given the problem is x. When time equal to 0, the vertical displacement is 0. U. Here U is vertical displacement, if I haven't mentioned it yet. So you just what you just get is, okay, you have u x 0 equal to summation n equal to 1, time equals 0. You have an. When time equal to 0, you have cos of 0 plus bn sine of 0 sine nx. Then you have ux 0 equal to summation n equal to 1 to infinity. Then you have an sine nx has to be equal to 0. Okay, then from here, an is just the Fourier series for the coefficient, which is 2 over pi, 0 to pi. The function 0 sine of nx dx just gives you 0. Okay, with an being 0, you have u xt equal to the summation n equal to 1 to infinity. N is 0, so you are left with bn sine of a and t sine of nx, like that. Okay, now I need to find bn again. I use the other initial condition. Going back, okay, this is the other initial condition. Was given that first derivative u with respect to time when 0 equal to sine x. Let me just confirm if it is t equal to 0. Yeah, t because initial condition. Okay, t equals 0. I find the derivative from here, u delta t. Notice that I'm just finding derivative respect to time. So it's going to be derivative respect to time of the summation n from 1 to infinity bn sine of a and t sine of nx, like that. So derivative u with respect to t is going to be summation n1 to infinity. Then it can go in the derivative term and it will just bn is a constant, sine of nx is a constant of sine of a and t, because it's just from derivative respect to time. So du delta t is going to be summation from n1 to infinity bn sine nx. Here you have a and cos a t, like that. Remember that, okay, delta u delta t when t equal to 0 equal to the summation bn times a times n. T equal to 0, cos of 0 is 1, and you have sine nx. has to be equal to sine x, which is the initial condition. From here, it is just a Fourier series, again, where all of these is your constant, like Cn, and this is your fx, a function. So you have that your big Cn, 2 over pi, 0 until pi, fx sine nx dx. This comes here in the formula. Now you have 2 over pi, 0 until pi, fx is sine x, then you have sine nx dx, like that. Okay, now you just need to find what is Cn. Cn is a times n times bn. 2 over pi, 0 to pi. Remember, what is sine? You have to remember that sine A times sine B equal to cos A minus B minus cos A plus B divided by 2, like that. Yeah, this is from trigonometry. Yeah, and you pretty much have to know. If you don't remember, then, well, yeah, you just have to know to solve this integral. That's how. Okay, I'm gonna move to another line to give space. I have bn times a times n equal to 2 over pi integral 0 until pi cos of x minus nx minus cos of x plus nx divided by 2 dx. Then you have bn times a times n equal to 1 over pi 0 until pi cos x 1 minus n minus cos x 1 plus n. Dx, like that. Okay, now you just need to integrate this. Okay, you just need to, in this case, you just need to integrate. But the point is, this is going to depend on n. This is going to depend on n. Okay, we're going to see that later. Okay, just integrate bn times a times n equal 1 over pi. Then you have sine x 1 and 1 over n is a constant minus sine 1 plus n times x 1 minus n again is a constant 0 until pi, like that. Now notice that actually this solution is going to depend on how the n is changing. For example, if n equal to 1, then here we get sine of 0 over 0, right? We have sine of 0 over 0. But if n different than 1, we just get sine of some number. For example, can see 2 over, for example, 2, and then we sub pi, then we can solve. But we have a problem when we put n equal to 1. So I'm going to evaluate this integral for n different than 1 first. For n different than 1, I have bn times a times n equal to 1 over pi. I have sine of pi times 1 minus n divided by 1 minus n minus sine of 1 plus n pi divided by 1 plus n. This is going to be just some number, some number, some number. So sine of pi is 0, so everything just gives you 0. So you have bn equal to 0 for n different than 1. Now, for n equal to 1, I have to evaluate. But if I just add here, it's kind of hard to evaluate here. So what I'm going to do is like, okay, I will go back here to this initial formula. Bn times a times n, which was the Cn, is 2 over pi, integral 0 until pi, sine x, sine of nx dx. Okay, if n equal to 1, then I have b1 times a times 1 equal to 2 over pi, integral 0 until pi, sine x, because n equal to 1, dx. Then you have 2 over pi, 0 to infinity, sine squared x dx. That means a times b1 equal to 2 over pi. Now I just need to solve this integral. 0 until pi, 1 minus cos of 2x divided by 2 dx. Then you cancel this. Then you have 1 over pi, integral 0 until pi, 1 minus cos of 2x dx. A times b1 equal to 1 over pi, x minus 1 over 2 sine of 2x. Evaluate from 0 until pi. 1 over pi, when I sub pi, it gives me pi. Sine of 2 pi is 0. Minus, when I sub 0, everything is just 0. Then everything gives you pi over pi, which is 1. Isolate b1. b1 equal to 1 over a. So you pretty much you have as an answer bn equals 0 for n different than 1. And you have b1 equal to 1 over a for n equal 1. Now I go back to the solution. Let me just find it, which is here. I have that an was 0. an was 0. So the general solution, I'm just left with uxt summation 1 until infinity bn. Then I have sine of n. Let me just go back to the general solution. ant t times sine of nx. Like that, the general solution. Where bn is given by this. Then this is the same as saying, okay, b1 times sine of n equal to 1, right? N equal to 1, at sine n equal to 1 x plus summation n equal to 2 infinity of bn times sine nat sine nx, right? So I just developed when n equal to 1 plus when the summation of the rest. But the point is, when n different than 1, everything bn just becomes 0. So everything gets cancelled. So you are just left with uxt, which is equal to b1 sine at times sine x. Then what is b1? 1 over a times sine at times sine x. So your general solution in this case is just, okay, uxt 1 over a sine at sine x. Okay, that's your general solution. And that's how you actually solve a wave. Let me just go back, a wave equation. The procedure is just the same. You just separate and then you evaluate the boundary conditions. Just see, okay, the boundary condition, you have 0 boundary condition, 0, 0. So you just can separate immediately. You just separate them and then do the other steps, evaluate, and use the initial condition to find the constants. For wave equation, we end up with two constants. So you have to evaluate both constant and then just write the general equation. And that's all for wave equation. For next video, I will solve maybe one more wave equation or move to Laplace equation.